Hello everyone, this is Ivan, and today I would like to propose you to talk a little bit about signal detection. And today we will discuss a threshold value selection based on value of errors of some mistakes. And of course, we will use Matlab as the most advanced tool for simulation and getting improvement of our theories and formulas. Mostly today we also consider civil aviation, and uh, we will talk about radars and about different probabilities of radar uh, detection, of target detection by radar, sorry. And let's start. Okay, that's why if you remember the main theory about radar, and uh, up to now it doesn't matter which type of radar or even which sensor we will discuss, because uh, if you use radio channel for measuring something, we always can apply uh, this theory for signal detection at the radio communication channel. However, we will consider signal detection in some kind of radar equipment. That's why radar, it is a specific device which we can use to detect location of some objects in the airspace. And the main idea of radar operation means that we've got a transmitter with a directed antenna, and then this transmitter can generate specific radio pulse and then apply this radio pulse to the antenna. Then this signal will be uh, radiated from the antenna element and will propagate in the airspace. Due to directional characteristic of this antenna system, we can transmit signal directed at some particular direction. Okay, and after the signal propagation, probably this signal can meet some metal construction or materials that can conduct electricity. And in this case, these objects with such kind of physical structure can reflect radio waves in the opposite side. Of course, such objects can reflect in different sides. However, some part of energy come back to the radar. And based on that, radar can measure the distance to the object, and by time of traveling signal in space to the object and return to the radar, and by direction characteristics of antenna system, because we know current direction of antenna system, and mechanically we can route this antenna location to the computer-based system to get precise coordinates of detected object. And one of the quite important problem in radar, which level of threshold value we need to use to correctly detect presence a reflected signal uh, in their uh, input of receiver, because signals which we get back from reflection is quite poor by amplitude, and in this case we need to find compromise between different parameters of optimal detection. However, today I would like to talk with you only about basic principles of signal detection uh, in their noisy environment. Therefore, let's imagine that at the input of receiver we have correct signal, which is S. Like we've got signal S, it means signal, and we've got some random noise. And usually in radio we can use different types of noises, and it based on different like nature. And uh, today we will talk about Gauss noise. Um, However, up to now it doesn't matter. That's why at the input of our receiver we've got U, which is like a voltage, which is equal sum of signal, reflected signal. The form of this signal we don't know, and some noisy component. If we can represent it in the form of graph, here you will see that we've got time because the signal will be different in time. We've got amplitude, and we've got signal, which is the red one. It was probably radio pulse. However, after the propagation, this radio pulse has been damaged a lot, and it looks like something like that. And due to presence of noise uh, in the radio communication channel, which we use for transmitting and receiving, this noise will be just summarized to our correct signal S. And this noise is just uh, additional component in our channel. That's why we've got some voltage. And usually the most types of detectors at the basic level uh, have to detect presence of signal, of correct signal, in their very damaged like nature. And in this case, in the most simple way, we can just can use some level of voltage, and if the level of voltage will be crossed by our signal, we can fix that we've got correct signal at that time. And in any radio navigation equipment, basically we use the same principle. Okay, and the question which I would like to discuss with you today, how we should select threshold value, and what kind of approaches we need to consider when we talk about threshold value for correct signal detection. In this case, we can consider four different probabilities, and we will discuss mostly this task in probability level, because usually we would like to minimize errors of our detector. That's why probability it is a good indicator for correctness of our system operation. That's why I've got a table where I've got four types of probabilities. I've got description of these probabilities, and I've got two columns. First column will indicate if radar detect presence of object or it cannot detect. And the next column will present if uh, if our signal or reflected signal, if it is radar equipment, was present in their input value or it was absent. That's why next let's discuss these four types of quite important probabilities for any detectors. First probability is P11. It's called P11 because we've got two yes. Okay. Uh, in logical form, yes can be assimilated to true, which is logical one. Okay. That's why P11. It means that reflected signal is present in input of our antenna and radar correctly detect presence of this signal. And in this case, we can get probability of correct detection of signal presence in the input signal. Okay, and at the same case, let's consider the last probability P00. It means that we don't have correct signal in the input and rather correctly detect that signal was absent. It means this probability is probability of correct decision about absence of signal. And based on that, we've got two next probabilities. Next one, probability. It means reflected signal was present or correct signal is present. It means S is present in our input. However, radar decision was false because radar cannot detect it. Probably this signal was quite poor and it cannot cross threshold value. That's why radar or detector cannot see this signal in their noisy environment. And in this case, this probability called target omission. It means that we missed our correct signal, however it was present. And usually uh, it may happen in two cases. When signal was damaged a lot or noise are very or noise has valuable amplitude and this noise just masks our correct signal. And also the second probability P10. In this case we don't have reflected signal, we don't have correct signal. However, detector provide us decision about presence of the signal in their uh, input of our receiver. And in this case, we called this probability 10 false alarm. It means we detect presence of signal, however, it was not present in data channel. Two of these probabilities, usually called risks or errors, because uh, because they are connected with something bad. That's why first probability, it may be a risk of target omission, or the second one, it can be risk of false alarm. Also, they can call by errors: error of target omission and error of false alarm of our detector. That's why this classification can be applied not only for radars and detection of targets, it also can be applied for any detector in radio communication channel. The same idea for radio pulses identification, or maybe, okay, whatever you would like, any navigation system you can use. And also we've got the same problem with correct signal detection at the noisy environment. Okay, let's go next. Okay, just a second. Then, if we can represent our noise in form of Gaussian noise, in this case, we can draw line, horizontal line, as an voltage line, and if we do not have any signal, it means that it was correct signal is equal to 0 because it is absent. We can fix probability density distribution of noise with 0. It means that our probability density function describes probability of reaching or getting some value of noise. It means that the more frequently in the channel, noise will be close to the 0, and the small and more valuable fluctuation of voltage based on this probability will be much more rare than uh, quite small events near the 0. That's why probability density function, probability function show us probability, and probability density function, it is the same with probability function. However, it was scaled to get area under the probability density function equal to 1. That is very helpful if you would like to estimate confidence band. Okay, next, if we have some correct signal with level S, let it be voltage of or amplitude of our correct signal. Then we can also apply normal probability density function associated with this signal level. It means that if we measure signal, this random variable will be added to our signal level. And in some case it will be added, in some case it may be minused. And if we would like to reach correct detection, we need to specify our threshold value somewhere between 0 and S, or maybe even more than S. It depends on amplitude of noise. Okay, also here I've got the same table from previous slide because I would like to make visible for you titles of probabilities and special errors which we will analyze next. Okay, as you can see from this picture, from geometry of two probability density functions, and usually these probability functions called as probability density function of signal absence and probability density function of signal presence. Therefore, if you would like to get probability that probability of correct decision about absence of signal, P0, 0. It means we need to count probability that decision will be false. It means there is no detection. In this case, we need to count an area under the probability density function at their distance from minus infinity up to our threshold value u0. Therefore, probability density function, it is function that has area under this function between this shape of function and axis x. Okay. In our case, it is voltage, however, it doesn't matter. And area under this function will be equal to 1, which is equal to 100% probability. And probability of being in some particular interval, it will be area under the probability below probability density function. And to get probability of correct decision, we can just easily get an integral, because integral is geometrical representation of area under the function. That's why integral from minus infinity up to u0 from our probability density function by du, by voltage. Then P10, it will be probability of false alarm. Probability of false alarm, it will be we do not have signal present, however, system detected. It means that noise was much more than our threshold value. And to count probability of false alarm, we need to get integral from use O from our threshold value plus up to plus infinity. However, we know that two of these probabilities, 0, 0 and false alarm, compose a full group of probabilities. It means that it can be only one possible. It cannot be happen both of these cases. That's why two of these cases we called full group of probability, because sum of them is equal to 1. That's why in this case this probability of false alarm we can estimate as 1 minus probability of correct decision about absent signal. Next, Let's consider in the same way probabilities of target omission. However, in this case, we need to use probability density function of signal and not noise or absence of signal. That's why in this case, probability of target omission or risk of being omitted, it is area under the probability density function of present signal from minus infinity up to u0. It means below the red probability density function. And in this case, we can represent it in form of integral as well. That's why it will be integral from minus infinity up to our threshold value, then probability density function of correct signal. That's why please take attention that here is a raw signal, it means red one, and here raw noise or absence of signal. And in this case, mean value is equal to 0 and it means green line. That's why rho m is green line, rho s is the red line of probability density functions. And we've got one addition probability of correct detection in case if we've got this signal. And this probability forms a full group of probabilities, full group of event with target omission error. That's why we can count it like 1 minus p01. If someone forget, I've got formulas for normal probability density functions. This is like Gaussian probability density functions. And you will see that in these functions we use mu signal and mu noise. Mu noise is equal to 0. However, in some system, mu of noise can be not equal to 0. It can be a little bit more because in particular radio channel we can get already some level of signals that may be result of interference or some other effects in radio waves propagation. Okay, and probably that's all about theoretical level. Now I would like to propose to follow me in mass modeling in Matlab, and also as previous time we try to count for these probabilities for different conditions and try to build graphs for dependence of our threshold value. Okay, maybe not threshold value, we will talk mostly about probabilities. That's why we will count for probabilities based on different voltage, and we will see how it works. Voltage or threshold value. That's why next I will switch to Matlab. I've got it already switched on in order to minimize our time. Just a second. And also as well I will try to use two approaches in order to verify our obtained formulas, because formulas of getting these probabilities is quite useful However, it will be better if we approve these formulas by statistical modeling. That's why I've got already prepared script in Matlab. Then I just need to prepare environment of Matlab. I will use CLC clear bars, close all because I like many pictures and visualization. Then I would like to specify, first of all, input data for our simulation. And first of all, let's specify mean value and sigma for our probability density functions of absence of signal and presence of signal. That's why I will use mean value of noise. Let it be equal 0 in initial condition. However, signal I would like to set up, for example, for some particular value 100 and let it be some value in millivolts. Then, what about sigma? You know that sigma it is the description of noisy environment. And this sigma, okay, sigma it is a mean square deviation error. And this sigma, it is quite valuable parameter of probability density function because it guides a shape. It means that if sigma will be okay, will have one value, the shape can be quite slim. However, for big values, shape can be quite wide. That's why I will specify sigma and pay attention that we will use the same sigma from probability density function of signal and probability density function of signal absence. And in this case, sigma will be equal, let it be approximately 3 times less than our correct signal. That's why I just multiply 0.3 with our correct signal. Okay. Next, let's specify threshold value, and let's specify like a matrix for different threshold values, and it may be logical to use a range for threshold value to be placed between mean value of noise and mean value of signal, because in this case it means that we can select different threshold value, and also in this case it will be in millivolts. That's why this line creates us matrix U0 with many elements from 0 to 100 with 0.1 step. And probably that's all that we need to start computation. Next, we just need to apply functions to estimate this integral. However, in Matlab, everything is quite easy because we've got predefined this function in Matlab. And in order to see that, I would like to show you. Therefore, I will use Google and I will type Matlab norm CDF. CDF, it is normally cumulative distribution function, and if we click on it, you will see that it has norm CDF. We need to specify input value x, then mu and sigma, and we got our values. However, I would like to scroll it down where we've got description of this function, and just a second, yep, you will see that in this function we've got exactly integral from our normal probability density function. That's why if we can compare, you will see it is the same with this function, and with integral, pay attention always with the limit value. And here we got minus infinity with x, and in our case it is u0. It means that we can use cumulative distribution function to count our probabilities. Therefore, I will close this one and just type that P00 is equal norm CDF, normal cumulative distribution function. Then we need to specify U0 because U0 is here. So for U0, then I need to specify mean value for noise because it is raw noise, and raw noise is green, and mean value is equal to 0. Therefore, in our case, we use mean value for noise. Then also we need to specify sigma, which will be the same for both absence of signal and presence of signal. That's why we've got. Next, P10 can be estimated quite easy. P10 is equal to 1 minus P00. Okay, and next, P01 is equal norm CDR, sorry, for probability density function of present signal, and in this case mean value is equal to signal. In our case, the signal is S, 100 millivolts. Therefore, I will put S. Oh, sorry. I will put our up boundary U0, then comma, and then I need to specify S. And then just add sigma, because it is the same. We will use the same shape of probability density functions. And then we can easily count probability of correct detection in case if signal was present, which will be 1 minus P01. Okay, we've done it. Congratulations. After running of this code, if we don't have any mistakes, we will obtain distribution of all of these probabilities from threshold value U0. Let's plot a graph figure, and you know that many students ask me why you type color white. Okay, because okay, I like white because all Windows by default is white. That's why I like white. And also when you copy it to some reports probably, or in some Scholar articles, much more better will be if this picture will have white background, because in this case it will be normally integrated into the white side of the paper. That's why I will specify color. If you don't want, you can just miss. And however, in this case, you do not need to write white. You can write white or can just use W because W it is a short title of white color. However, next I definitely recommend to specify name of figure because it helps you later if you save it. And I will use title, let it be analytical threshold estimation. Okay, let it be threshold value. Okay, next I will use just plot because we do not need to apply some other graphs. And by x-axis it will be u0, and by y let it be first u0, 0. However, I like in percentage, that's why I will multiply it with 100. Then let's specify color, let it be dashed red. Okay, probably let it left like this one. Then U0, it will be next sequence of probability, multiply with 100. Yep, and let it be dash dotted green line. Then let it be probability P01 multiplied with 100, and let it be solid blue line. And finally, let it be U0 P11 multiplied with 100. And in this case, it will be okay, solid magenta line. Then I will recommend also use title, okay, because it is good if you've got all titles and all descriptions of any axis. That's why X label. Sorry, got typos. And at X label, we've got voltage with lowercase 0. And this voltage will be in millivolts. Okay, next let's specify Y label. And Y label, it will be probability, or just P, in percents. Because we multiply with this 100. That's why we got probability in percent. And also let it be legend, where we just put titles of these probabilities. That's why P 0, 0, then P, okay, P 1, 0, then P 0, 1. Okay, this type of brackets is used to specify that all further sequence inside of this brackets will be lowercase, because here is a sign of lowercase. And finally, the last one, it will be probability of 1. Okay, also I like grid on, so grid on, and also let's specify limit value for axis by x limit. And here we specify minimum value for voltage 0 and maximum value of u0. Okay, and I think this is time to run my code. After clicking run, okay, sorry, probably I've got mistake. Let's check. Norm CDF. Norm CDF. Cumulative distribution function. It was my fault. Sorry. And where is the graph? Arrow undefined function or okay. Let me check. Okay. 0. Okay. Let it be resimulated. And I've got my graph. However, I've got a mistake. Probably with let's read it. Okay, title. Sorry. Title typos. Let's do simulated one more time. Okay, and now we have everything correct. That's why we've got probability by probability distribution by y axis. Then we've got threshold value in millivolts across the x-axis, and we've got different types of probabilities. Next, let's try to approve these formulas by statistical modeling, because statistical modeling is another possible way for obtaining the same data. That's why in the statistical modeling, we will use another approach. We will simulate multiple signals and multiple noise, and then add both of them and try to compare it with the threshold value and estimate probability as a frequency of obtaining particular amount of data. Therefore, I will create new section of my code, which will be statistical modeling. And in this case, I will need to specify number of iteration or number of input values that we simulate for each iteration. And in this case, first of all, we can use small value 100. Later, we can increase it after the checking our software. And I will use 4 because in this case it will be very spectacular, which will change threshold value. Therefore, I will do something like that. If you use for, always please put and. Hope you remember it. And inside of loop, we put part of code which we repeat. And we will use noise, which will be generated by norm rnd function, which also have mean value for noise as an input and sigma value. And then we also need to specify a size of matrix which will be returned from us for us. It will be one row and n columns. Then we will do for signal. Signal is equal norm rnd. Sorry, norm. Yep, norm rnd. Here we need to specify signal s and sigma and 1 and n. Okay, next let's count statistic. Let it be n1. Number of elements which will be result of finding noise less than our threshold value. Therefore, I specify address of this threshold value. And then we can easily count PS. S will be like statistical 0, 0. In this case, it will be indexed by I. And n1, we need to divide to n. And then n2, it will be a number of elements which we will find in case of matrix signal will be less than U0 from I. And letter be statistical 0, 1. Also use index addresses I, and then m2 will be divided by n. And finally, at the end, let me calculate all other probabilities. PS10 is equal 1 minus PS00 and PS11 is equal 1 minus PS01. However, before we will compute it and run it for simulation, okay, I would like to plot a graph like that based on normally distributed, like absent function and present function. That's why I just would like to plot two of these PDFs, however in statistic that we have. And to do that, we can easily use histogram function. Therefore, I just copy the figure, okay, and let it be noise and signal histogram. And I will use function histogram. You see, this is quite easy, and specify just matrix noise. That's all that I need. Then I will hold on this figure and plot histogram of our signal. And I will put hold off. And next, I just would like to specify X label, Y label, and title. Therefore, it will be X label. Label, it will be threshold value. O0. Then Y label. It will be frequency. Frequency of occurrence. Yep. And let add title. Which will be the same with our name of our figure. Okay, let's try to simulate it. And we will have something like that. If you would like, you can also add grid in. And it will be with a grid. And here we've got two histograms of absent signal 0 and present signal 100. And it looks like this one. Due to a small amount of sample, we've got quite different probability density function. That's why in this case we need to increase number of randomly generated values to get more reliable data. And finally, let's plot the same figure that we got from analytical formulas to prove them. However, in this case, we will change analytical to statistical threshold value estimation. Okay, and what we need, we just need to change pay 00, just adding s, which in our case means statistical. And that's all. Okay, let's resimulate all of that, and we obtain the following results. Just a second. Therefore, okay, just a second. I just try to minimize what I have. Therefore, here we've got analytical, okay, dependence of all of these errors based on our threshold value O0 and statistical threshold detection. And as you can see, then statistical fully approve our analytical formulas. It means that our formulas is correct. If you can consider our formulas, you may see that, okay, maybe this one I will open. You will see that if we increase our threshold value from 0 to S. Our P00 or correct decision about absent signal, it is the red one, will increase. That's why by increasing threshold value at the site of signal level, probability of correct decision about absent signal at 0, 0 will increase. And at the same time, okay, it means true because okay, we just move this dashed line in this side. Yes, of course, because this area will be bigger and bigger. However, at the same time, probability of false alarm P10, it is green one. Yeah. Is going down. Yes, it is also logical because it is a full group of dependents. And the same one for other group. It is P11 plotted by magenta is a probability of correct detection, and P01, it is blue one, probability of target emission. What is quite important here, that usually scholars, in order to get efficient detection of correct signal, use a middle one between errors. Because in any system, we would like to minimize errors. And in this case, minimal errors will be at point of crossing lines of probability of false alarm and target emission. And this value will be exactly at the middle between these lengths. That's why this point of crossing means efficient point to get equal probabilities for target emission and false alarm. However, in some particular case, based on how many times we will get our correct signal, we can change a little bit, and we can move in one side or in other side in order to base in order to have more suitable values of probabilities of correct decision about present signals, or probabilities of correct decision about absent signal. Next, what I also would like to show you, if you can see in statistical approach, we've got quite noisy results. In order to minimize this fluctuation, we can reduce it by increasing size of learning sample from 100, for example, to 2000. And if you run it again, you will see that our error become much more welcome, much more suitable for our analytical dependence. Probably that's all for today. Also, I will be glad if you try to remember that in case of good detection at the simple like environment and in simple case, we can use middle value for threshold uh, value between mean value of noise and mean value of correct signal. However, okay, in some case we need to know uh, the mean value of correct signal, which will come back for us. However, in many cases, if it is radio channel, we can use some models to simulate radio propagation and attenuation during the radio waves propagation. That's why actually we can know this mean value. And in order to minimize two of these errors, we can select the middle between mean value of noise and mean value of correct signal. That's all for today. Thank you for watching me, and uh, I was glad to represent you what I have. Therefore, thank you very much for watching. See you again somewhere. Good luck.